In this video, we're going to determine the rate law for an experiment involving nitrogen monoxide and ozone. When approaching these problems, it's always best to start off by finding two experiments where the concentration of only one reactant changes. It doesn't matter which reactant you pick, whether it's nitrogen monoxide or ozone in this case, but that the other reactant concentration is held constant. And we'll see why that is in a second. To set this up, we're going to take the ratio of two experiments. In this case, I'm going to solve for ozone's rate law first, and I'm going to do it by comparing experiments 2 and 1. So we set this up by saying the rate of experiment 2 relative to the rate of experiment 1 is equal to the rate constant of experiment 2 over the rate constant of experiment 1, which happens to be the same value, over the ozone concentration of experiment 2 over the ozone concentration of experiment 1 raised to some power x. We don't know what x is. And then we're going to do the same thing for nitrogen monoxide, NO of experiment 2 over NO of experiment 1 raised to some power y. Now we can start plugging in our actual values. So 1.32 times 10 to the minus 4th over 6.6 times 10 to the minus 5th equals the rate constant k divided by k, so that goes away, becomes 1 because it's the same value. And then we're left with ozone's molarity of 6 for experiment 2 divided by experiment 1 raised to some power x. And then with nitrogen monoxide, they're both going to be the same value. There we go, raised to the power of y. And since we know this is 1 raised to any power is still going to be 1, so that doesn't become a problem. Here we've got 2 raised to the x is equal to 2. So going ahead and I'm going to scroll down a little bit here. We'll find that 2 equals 2 to the x, because 1 raised to any power is 1, and 1 times 2 is 2 to the x. So now we can solve. We can solve by taking the natural log of both sides. So ln of 2 equals x ln of 2. Solving for x equals 1. So we now know this reaction is first order with respect to ozone. So we can start to write the rate law. Rate equals rate constant k, ozone raised to the first power, nitrogen monoxide raised to some power y. So now what we have to do is go back and repeat the same sort of procedure, except this time having ozone held constant and finding an experiment where two nitrogen monoxide concentrations are different. So I'll go ahead and set that up here in a second, and we'll get going. So I've cleaned this up a little bit, and we now have our rate law, but we can pick two different experiments to compare. So rather than using 2 and 1, what we can do is look for an experiment where NO is changing. So I'm going to pick experiments 4 and 3 to compare. So get this set up here. So we've got 3.96 times 10 to the minus 4th over 1.98 times 10 to the minus 4th equals ozone, which is 9 times 10 to the minus 6 in both experiments, raised to the first power, times Experiment 4, 2 times 10 to the minus 6 molar over 1 times 10 to the minus 6 molar raised to some exponent y. We go through and plug and chug. We find the ratio of the rates is 2. 1 raised to the first power is 1 times 2 to the y. In this case, we find that y is equal to 1. So we say this reaction is first order with respect to nitrogen monoxide and first order with respect to ozone. So let's write our overall rate law and then solve for the rate constant K. Since we found that both nitrogen monoxide and ozone are both first order, we can now write our rate law. So we can say the rate of a reaction is equal to the rate constant K times ozone raised to the power of 1, or that is ozone's first order. We have nitrogen monoxide also raised to the first power, making this reaction second order overall. Now we can pick any one of these experiments, 1 through 5, to solve for the rate constant K. It doesn't matter because all these experiments are done at the same temperature, therefore they should all have the same rate constant K. I'm going to go ahead and pick experiment 1 to solve for the rate constant K. 6.60 times 10 to the minus 5th, and that's equal to moles per liter times second, equals the rate constant K times ozone, which is 3 times 10 to the minus 6 molar, times 1 times 10 to the minus 6 molar. And now we can solve for K. Now I'm going to do a quick correction here. Moles per liter times second is really the same thing as molarity per second. And that'll just help us get the units right on this. So, solving for K, we get 6.6 times 10 to the minus 5th molarity per second equals 3 times 10 to the minus 6 times 1 times 10 to the minus 6, so we get 3 times 10 to the minus 12 molarity squared times the rate constant K. If we divide both sides by 3 times 10 to the minus 12, what we find is we get 2.2 times 10 to the 7th, 1 over molarity times seconds, because of our units and how they cross-cancel when we work them through, and that's equal to the rate constant K. So our final rate law expression is rate equals 2.2 times 10 to the 7th, 1 over molarity times seconds, times ozone raised to the first power, times nitrogen monoxide raised to the first power. And thus we've completed our rate law for this experiment.